Welcome, everyone. I'm excited to kick off today's presentation on magnetism. Today, we'll explore the fascinating forces behind magnetic fields, how they work, and their applications. Over the next few slides, we'll cover the basics, some interesting phenomena, and real-world uses. So let's dive into the intriguing world of magnetism. Let's begin by examining the comparison of dia, para, and ferromagnetic materials. These materials differ significantly in how they respond to magnetic fields, which is crucial for many applications. Diamagnetic materials are repelled by magnetic fields, whereas paramagnetic materials are weakly attracted. Ferromagnetic materials, on the other hand, are strongly attracted and can retain magnetization even after the external field is removed. Understanding these differences helps us select the right material for specific magnetic purposes. Next, we'll look at a bar magnet and its dipole moment. A bar magnet produces a magnetic field with a north and south pole, and the dipole moment is a vector quantity that describes the strength and orientation of this magnetic source. This concept is fundamental because it helps us quantify and analyze magnetic fields in a more precise way. Moving on, terrestrial magnetism refers to Earth's magnetic field. It's generated by movements within Earth's outer core and behaves like a giant bar magnet, though it's not perfectly aligned with Earth's rotational axis. This magnetic field is vital for navigation and understanding Earth's interior processes. Now, consider the current in a solenoid. When a current flows through a coil of wire, it creates a magnetic field similar to that of a bar magnet. In fact, a current-carrying solenoid can be seen as an equivalent model for a bar magnet, which simplifies the analysis of magnetic systems. As we conclude with the end of magnetism, we recognize that magnetic phenomena have limits and boundaries, which are essential for understanding magnetic material behavior and designing magnetic devices. We'll also discuss hysteresis in magnetism. Hysteresis describes the lag between changes in magnetization and the external magnetic field, leading to a hysteresis loop. This concept explains how magnetic materials retain some magnetization even after the external field is removed, which is important for magnetic storage. Next, we cover important terms in magnetism such as magnetic field, flux, and magnetic permeability. Comprehending these terms provides a solid foundation for analyzing magnetic systems and their behaviors. Then, we look at the current loop as a magnetic dipole and the associated dipole moment. A current loop produces a magnetic field similar to a tiny bar magnet, and the dipole moment quantifies this magnetic effect, linking electric currents to magnetic phenomena. Following that, Coulomb's law in magnetism describes the force between magnetic poles, analogous to electric charges. It helps us understand how magnetic poles interact and influences the design of magnetic circuits. Finally, we arrive at the properties of a bar magnet. Key properties include having a magnetic south and north pole, producing a magnetic field, and exhibiting properties like magnetic attraction and repulsion. These properties form the basis for many practical applications in navigation, electric motors, and magnetic storage. By understanding these core concepts, we build a comprehensive picture of magnetism and its significance across various scientific and technological fields. Magnetism is a fascinating phenomenon where certain substances, like iron, nickel, and cobalt, are attracted to each other. When a body has this property of attracting these materials, we call it a magnet. Now, a magnet has specific points called magnetic poles, which are typically located near the ends of the magnet where the magnetic force is most concentrated. Interestingly, the Earth itself is a natural magnet, which is why compasses work. They align with Earth's magnetic field. This magnetic field is the region around a magnet where it can exert forces on other magnetic objects or iron. Understanding these concepts is crucial as we explore how magnets work and their applications in our daily lives. Let's talk about the concept of repulsion as a test for magnetization. Now, while a magnet attracts an iron rod or the opposite pole of another magnet, this attraction alone isn't a definitive test for magnetization. Why? because non-magnetized iron can also be attracted. However, if a rod is strongly repelled by a magnet, that is a clear indication that the rod is indeed magnetized. Repulsion is a more reliable sign because only magnetized objects exhibit that kind of repulsive force. Next, let's consider magnetic poles. They always come in pairs, north and south, and these poles cannot be separated. You can't have just a north pole without its south counterpart, and vice versa. This pairing is fundamental to how magnetic fields work. Moving on, magnets attract magnetic substances like iron, cobalt, and nickel. This is a key property that helps us identify magnetic materials. Now, an interesting aspect is that unlike poles, north and south, attract each other, while like poles, north or south and south, repel each other. This interaction explains a lot about how magnetic forces behave and how we can use magnets in various applications. Also, magnets have the ability to induce magnetism in other magnetic substances. So, even if a material isn't initially magnetized, bringing a magnet close to it can temporarily magnetize it. Finally, when you freely suspend a magnet, it naturally aligns itself along the north-south direction. This is because of Earth's magnetic field, which acts like a giant magnet guiding the magnet's orientation. All these properties are fundamental to understanding how magnets work and their practical uses in everyday life and technology. Now let's look at the uniform magnetic field on the plane of the diagram. As you can see, the field lines are evenly spaced, indicating a uniform magnetic field. When we consider the field perpendicular and into the plane of the diagram, it means the magnetic field is directed inward, away from us. Here's a helpful tip. When you observe any one side of a current-carrying loop, if the current flows in an anti-clockwise direction, that side behaves like a magnetic north pole. Conversely, if the current flows clockwise, that side acts like a magnetic south pole. This is key to understanding how loops generate magnetic fields. Now, focusing on the current loop as a magnetic dipole and the concept of the dipole moment, we see the uniform field is perpendicular and emerging out of the plane of the diagram. Representing the uniform magnetic field, remember that the SI unit is the ampere meter squared, written as a M2. The magnetic dipole moment, which we denote as M, is defined mathematically as the product of the current I, the area A of the loop, and the number of turns N. So, M equals I times A times N. This dipole moment essentially characterizes the magnetic strength and orientation of the current loop, linking the physical current setup to the magnetic field it produces. Understanding this helps us see how current loops behave like tiny bar magnets, with a distinct magnetic moment pointing from the south to the north pole of the loop. Let's take a moment to play around with the previous and next field lines. This will help you understand how similar they are, which is key to grasping the concept. Now, moving on to the main point of this slide, a current solenoid is essentially equivalent to a bar magnet. What this means is that when a current flows through a solenoid, it creates a magnetic field similar to that of a bar magnet. The field lines form closed loops, just like the magnetic field you see around a bar magnet. This equivalence is really useful because it allows us to analyze and understand magnetic phenomena in a more flexible way. Instead of thinking about permanent magnets all the time, we can use current-carrying coils to generate magnetic fields for various applications. So keep in mind, the key takeaway here is that a current solenoid can mimic the behavior of a bar magnet, which ties into our overall discussion of magnetic fields and their sources. Let's take a closer look at the magnetic dipole moment, which is represented by the formula M equals M times 2L. Here, M is the pole strength, and 2L is the length of the magnet. Essentially, this tells us that the magnetic dipole moment depends on how strong the poles are and how long the magnet is. Now, focusing on a bar magnet, the dipole moment is a crucial concept because it helps us understand how the magnet interacts with magnetic fields. The larger the dipole moment, the stronger the magnetic influence the magnet will have, especially in terms of creating a magnetic field around itself. This concept is fundamental because it links the physical properties of the magnet, its pole strength and length, to its magnetic effects. So, whenever we analyze magnetic behavior or design magnetic devices, considering the dipole moment gives us a clear measure of the magnet's influence. In the broader context of our discussion, understanding the dipole moment helps us grasp how magnetic forces operate and how different magnets compare based on their properties. The ratio of magnetic length to geometrical length is approximately 0.84, which means the magnetic length is slightly less than the physical length of the magnet. The magnetic length is defined as the distance between the poles of the magnet. When we talk about a pair of magnetic poles with equal and opposite strengths separated by a finite distance, we call this a magnetic dipole. The strength of this dipole, known as the dipole moment, is calculated by multiplying the pole strength, represented as m, by the separation between the poles, which is 2L. The SI unit for pole strength is ampere meters, m. The direction of the dipole moment goes from the south pole to the north pole along the magnet's axis. Now, the magnetic axis is the line joining these poles, and it's important because it indicates the direction of the magnetic field. Moving on, the geometrical length of the magnet is simply the straight line distance between its ends. And finally, the term geographic length relates to the overall length, but in the context of magnets, the key concepts are the magnetic length and the physical length, which helps us understand the magnetic properties and behavior of the magnet in various applications. Let's take a closer look at the force between magnetic poles. The constant K here is given by the ratio of μ0 over 4 pi, where μ0 is 4 pi times 10 to the minus 7 Tesla meter per ampere. This constant essentially helps us quantify the magnetic force in a standardized way. Now, the key relationship we see here is that the force, which we denote as F, is directly proportional to the product of the two pole strengths, m1 and m2. So, if either of these poles gets stronger, the force between them increases. At the same time, the force is inversely proportional to the square of the distance between the poles. That means as the poles get farther apart, the force diminishes quite rapidly, following the inverse square law. This relationship is quite similar to Coulomb's law for electric charges, but instead, it applies to magnetic poles. It highlights how magnetic forces behave in a predictable, mathematical way, which is fundamental to understanding magnetism in general. Connecting this to the overall theme, it shows us that magnetic forces, like electric forces, follow specific mathematical laws, helping us understand and predict how magnets interact at different distances and strengths. Let's take a closer look at some important terms in magnetism. First, we have magnetic field strength, or B. This refers to the magnetic flux density, which is essentially the number of magnetic lines of force passing normally through a unit area of a substance. Think of it as how concentrated the magnetic lines are in a given space. The formula B equals mu times H highlights that B depends on both the magnetic permeability, mu, of the material, and the magnetic intensity, H. Speaking of H, magnetic intensity at a point is the force experienced by a hypothetical north pole of unit strength placed at that location. It's a way to measure how strong the magnetic field is at a specific point, influenced by the pole strength and the magnetic properties of the medium. The relationship H equals B divided by mu shows how these two concepts are interconnected. By understanding these terms, magnetic flux density and magnetic intensity, we get a clearer picture of how magnetic fields behave and interact with different materials. These concepts are fundamental to grasping how magnets work and how they can be applied in various technologies. Let's take a closer look at the concept of μr, which is the ratio of magnetic flux density in a material to that in vacuum. It's expressed as B divided by B0, or equivalently, mu over mu0. This ratio essentially tells us how much a material enhances or diminishes the magnetic field compared to free space. Now, moving on to the term relative magnetic permeability, represented as μr. It describes how easily magnetic lines of force can pass through a particular substance. Think of it as a measure of the material's ability to support magnetic flux. The higher the μr, the more magnetic lines can pass through, indicating a more permeable material. The SI units for μr might seem a bit complex. It can be expressed in units like Tesla meters per ampere, Weber per ampere meter, or Henry per meter. These units help quantify the permeability in different contexts, but the key idea is that μr is a dimensionless ratio. Next, let's discuss magnetic permeability, symbolized as μ. This is a bit more fundamental because it measures the number of magnetic lines of force passing normally through a surface. In simpler terms, it reflects how much a material responds to a magnetic field. Its SI unit is the Weber, which is the unit of magnetic flux. Finally, magnetic flux, represented by the symbol phi, is the total magnetic field passing through a given surface. It's an important quantity because it helps us understand the total magnetic effect in a region. By understanding these concepts, μr, μ, and phi, we get a clearer picture of how magnetic fields interact with different materials, which is crucial for designing electromagnetic devices and understanding magnetic phenomena in general. Let's take a closer look at the magnetic meridian. At any location on Earth, the magnetic meridian is a vertical plane that passes through the magnetic north and south poles. It's important because it shows us how the Earth's magnetic field is oriented at that specific point. Now, moving on to the magnetic equator. This is a great circle on the Earth's surface that lies in a plane perpendicular to the magnetic axis. It plays a key role in understanding Earth's magnetic field because it represents the line where the magnetic inclination is 0, meaning the magnetic field is horizontal there. The magnetic meridian I just described is a straight line passing through the magnetic poles, but it's inclined at an angle of about 17 degrees to the Earth's geographic axis. This inclination is what causes the magnetic compass needle to deviate from true north. Speaking of the geographic axis, it's a straight line passing through the Earth's geographic poles, and it's also known as the polar axis. This is the axis around which the Earth rotates, defining the geographic poles and the equator. The geographic equator, which is the Earth's main dividing line between the northern and southern hemispheres, is a great circle on the surface of the Earth. All points along this line are equidistant from the geographic poles, which is fundamental in navigation and geography. Finally, the geographic meridian is a vertical plane passing through the Earth's geographic north and south poles. It helps us define longitude and locate any place on Earth in relation to Greenwich or other prime meridians. Understanding these concepts, magnetic and geographic lines, is crucial because they help us interpret Earth's magnetic field and improve navigation accuracy, tying into the broader theme of terrestrial magnetism and how it affects our daily navigation tools. Let's examine the comparison between diamagnetic, paramagnetic, and ferromagnetic materials. Starting with diamagnetic substances, these are materials that are weakly repelled by a magnetic field. Examples include antimony, bismuth, copper, gold, silver, quartz, mercury, alcohol, water, hydrogen, air, and argon. When such materials are placed in a magnetic field, the magnetic lines of force tend to avoid the substance, meaning they prefer to pass around it rather than through it. If you place a diamagnetic rod in a uniform magnetic field and suspend it freely, it will naturally align itself perpendicular to the magnetic field lines. Moving on to paramagnetic substances, these are materials that are attracted by a magnetic field. Examples include aluminum, chromium, alkali and alkaline earth metals, platinum, and oxygen. In a magnetic field, the lines of force tend to pass through these materials rather than the surrounding air. When a paramagnetic rod is freely suspended in a magnetic field, it aligns itself parallel to the field lines. In a non-uniform magnetic field, these materials move from weaker to stronger parts of the field, showing a feeble attraction. Finally, ferromagnetic materials are strongly attracted by a magnetic field. Examples include iron, cobalt, nickel, gadolinium, and dysprosium. The magnetic lines of force tend to crowd into these specimens, indicating a very strong attraction. When we place a ferromagnetic rod in a uniform magnetic field, it quickly aligns itself parallel to the field lines. If we consider ferromagnetic liquids in a watch glass, in a uniform magnetic field, they tend to collect at the center when the magnetic poles are closer and move away from the center when the poles are farther apart. To summarize, the key differences lie in how these materials interact with magnetic fields. Diamagnetic materials are feebly repelled and align perpendicular. Paramagnetic are weakly attracted and align parallel, and ferromagnetic are strongly attracted and also align parallel, but much more quickly. These distinctions are fundamental in understanding magnetic behavior across different materials. Let's take a closer look at the Curie temperatures for some common magnetic materials. For iron, the Curie temperature is around 1000 Kelvin. Cobalt has a higher Curie point at about 1400 Kelvin, while nickel's Curie temperature is lower, at approximately 600 Kelvin. Now, this brings us to an important relationship called Curie's law. It states that the magnetic susceptibility, which is a measure of how much a material becomes magnetized in an external magnetic field, varies inversely with the absolute temperature. In simple terms, as the temperature increases, the material's response to magnetic fields decreases. Mathematically, this can be expressed as being proportional to 1/T, or equals a constant C divided by T, where C is known as the Curie constant. This tells us that the susceptibility is inversely proportional to temperature. Similarly, if we look at the magnetization I in relation to the magnetic field H, it turns out that I is proportional to H/T, or I over H is proportional to 1/T. So overall, Curie's law emphasizes that the magnetic susceptibility of a material decreases as the temperature rises, highlighting how thermal energy disrupts magnetic alignment. This relationship is fundamental in understanding magnetic behavior across different materials and temperatures, tying into the broader theme of how thermal effects influence magnetic properties. Let's take a closer look at the hysteresis loop, which is represented by the loop ABCDEFA. This loop is fundamental in understanding how materials respond to magnetization and demagnetization. The area enclosed by this loop actually indicates the energy lost during each cycle, and this energy loss appears as heat. Now, the type of material plays a key role here. For instance, materials like iron, which have a thin hysteresis loop, are typically used for making temporary magnets. On the other hand, materials like steel, with a thicker loop, are suitable for permanent magnets because they can retain magnetization better. To completely demagnetize a material, that is, bring the magnetization intensity, I, down to zero, we apply an opposite magnetizing force. This force is represented by OC on the graph, and we refer to it as coercivity. Essentially, it's the measure of how resistant a material is to becoming demagnetized. Once we've reached the saturation level at point D, if we reverse the magnetizing force, the curve closes back towards point A, completing the cycle. This process illustrates how the magnetization responds to the changing magnetic field. The hysteresis loop also shows us that as the magnetizing force, H, increases, the intensity of magnetization, I, initially rises along OA and eventually reaches saturation at point A when we decrease H. I decreases too, but interestingly, it doesn't drop all the way to zero when H reaches zero. This residual magnetism, the leftover magnetization, is indicated by OB on the graph. In summary, the hysteresis loop not only demonstrates the relationship between magnetizing force and magnetization, but also highlights important properties like energy loss and residual magnetism, concepts that are crucial in designing magnetic materials and devices.